Hello, everybody. Yesterday, scheduling was our topic. We said that scheduling happens, the decision of scheduling happens when there are more than one process ready in our ready queue, and the schedule has to choose one of them because there is only, our assumption is there is only one CPU and only one process can use the CPU. That was the case. So several processes are runnable, and I need to choose one of them. So how do I make this decision? So the decision mainly depends on the environment. If you are running a batch system, a computer batch operating system, your decision might be different. If you are a real-time operating system, your decision might be different. And for the case of interactive systems, your decision depends on different criteria, because, as you know, different types of operating systems have different goals, have different parameters to optimize. Okay, so when we look at the scheduling task, the scheduling decisions, we have to know what is important for us. Okay, and that's why we are going to look at the scheduling algorithms with respect to the operating system types and with respect to what is important to us. So yesterday we talked a little bit about this, and maybe I think I gave you a few definitions, such as the definition of a CPU bound process and IO bound process. Okay, so in this is the nature of the processes. Some of them are CPU bound, some of them are IO bound. As an operating system designer, I don't get to choose which one runs on my system. Okay, I have to as an operating system, I have to accept whatever the application the user offers me, and I have to run it, I have to manage it, and I cannot say I like these kind of processes, I am going to make them run more, and etc. No, I have to be fair between them all the time. So one thing that we said is these IO bound processes, they tend to wait for IO for lots of times, maybe most of their lifetimes. They are waiting for IO to complete, so they don't get to use the CPU very often. They don't get to use the CPU for long amounts of time. That's why we need to be careful. Maybe we should give them more priority so that it is fair between these two kind of processes. Okay, so depending, as I said before, it depends on your motivations. If being fair is very important to you, then you have to be careful about this. Being CPU efficient is important for you, then you have to behave in a different way. Okay, so
Small question, sir. How does the operating system know what type of program is running, whether it's I/O or CPU bound?
well, I have their statistics, right? I have their statistics. I know how many times they caused page faults. Okay, page fault is not a bad thing. Page fault means that that process needs more data from the disk because of the memory optimization problems, or I know how many times that process needs IO, how many bytes it needed from the hard drive, how many times it stopped, how many system calls it is making. So I would know. Okay, when you do stuff like this, okay, these are all kept in the process table. When you look at this graph, and when you where is my, yeah, no, not this one, maybe this one. See, it says that this one used this many hours of CPU time, this one used this many hours of CPU time, this one used this many hours of CPU time, right? And you know when they started running, how much CPU they used. If you make a division, and you get what you need. Okay, some of them are very For example, this one, it needed lots of network traffic. Okay, although it didn't run much, it needed lots of network traffic, and I have these kind of statistics always kept in my page table. Okay, and that question will come back again. How do I know that this process is going to behave like that in the future, and etc. That's why, I mean, you don't try to be optimal with the scheduling, because you cannot see into the future. You can only guess by looking at the history of the processes. And we are going to have a few ways of looking at what the process did before. And maybe most importantly, sometimes we get this clue from the programmer. Programmer says that I have written a IO bound process. I have written a CPU bound process. Sometimes we get that information from the programmer, from the application itself. Okay.
Sir, may I ask a question?
Sure.
If we have a real-time operating system, what will be our priority in this case? We have an I/O process and we have a long CPU burst. What will be more important for us?
Well,
Because I see an example in the Stack Overflow for RTOS systems. They say that I/O will be lower as priority, and I couldn't get it.
well, usually, I mean, for the hard real-time systems, real-time systems, your I/O devices are very limited. For example, for the many I/O real-time systems, you don't have a hard drive, you don't have a mechanical drive for the real-time operating system. So everything has to be done. Everything has to be done between the CPU and the memory, and very fast I/O stuff, because the scheduling for the real-time systems is very strict. You cannot miss some of the deadlines. If you miss it, then your whole operating system is just junk. It is not useful. Okay, that's why their scheduling policies are very, very fixed. They say that, okay, I am going to, this is the real-time system, scheduling of a real-time system. They say that, okay, this is my timeline, this is T. I am going to divide this into this many slots, and process A has to run here, here, and here. Process B has to be here, here. C has to be here and here and maybe here. That's it. You are not going to change this order, and it's going to be this way. If I do this, I guarantee that C is going to run 3 times. Okay, there are no exceptions. A is going to run 1, 2, 3 times. B is going to run 1 or 2 times. I know that, okay? So there are no infinitely waiting, or there are no waiting for some very costly I/O to finish. Okay, if I am going to do this kind of scheduling, I don't get to choose many parameters. Okay, these are already decided during the system design time and during the design of these processes too. In real-time systems, you are not allowed to add your applications most of the time. Applications are written very, very carefully. Let's say each slot here 25 milliseconds. When they start, they have to finish in 25 milliseconds. No exceptions. In 25 milliseconds, you have to finish. Okay, so most of the time this process runs, okay, it uses 10 milliseconds and it says that, okay, I'm done. What happens to this area? It is wasted. You just wait. So most of the time you don't use 50% of your CPU time for the real-time operating systems. So the case is very different for the real-time systems. If you have the priorities in real-time systems, okay, and if you are trying to prioritize an I/O bound system process and a CPU bound process, you know that the CPU bound process is more predictable, because Anytime it starts, it has to finish in 25 milliseconds. For the IO bounds, they may have, they may need more than that time because they're going to do the IO later, maybe after they start running. So while I have CPU bound processes, let me run them if they are ready. Otherwise, I am going to let IO processes run. So that might be the logic. But as I said before, the I think the text that you read is talking about maybe soft real-time systems, because in real-time systems, hard real-time systems, usually there is no blocking because of I/O. Everything is ready when you are ready. And we will talk about the real-time systems when the time comes. Okay? And when we talk about real-time systems, as you're going to see, you don't have many alternatives for the scheduler. Schedule is always the same. You make decisions on the slots, okay, and each slot is used by one of the processes. And usually you leave some of the slots empty, so CPU is most of the time available for your processes. Okay, let me continue then. We said that again, depending on your operating system, motivations, your decisions might be different. Okay, so the IO request for the IO bound processes is so much. So what do we do to make things fair for these kind of processes? Maybe I should increase their priorities so that they get to use CPU more often than the CPU bound processes. Okay, so when do we make the scheduling decisions? Okay, after a fork, definitely. After you do a fork, what do I have? Now I have two processes, at least two processes. Okay, one of them is the parent, the other is the child. And both of them are runnable, right? Because I was running something. Both of them are runnable. Which one should I choose? That's an operating system decision. When one process says that, okay, I am done, I am exiting. Okay, in that case, which one is going to run? Again, another decision. When one process blocks and there are more than one process ready in the ready queue. When IO completes, what does that mean? If IO completes, there will be an interrupt, right? When IO completes, there will be an interrupt saying that IO is completed. So operating system will come in, will take care of the interrupt, will place that IO data in some memory location, and then since this was an interrupt, should I go back to the interrupted process, or should I go back to the process that needed this data? Okay, another scheduling decision. And sometimes after timer interrupts. What do we mean by sometimes after timer interrupts? Why do they say sometimes? What do they mean by sometimes? Are you guys hearing me?
Maybe sometimes it has a plan or a thing in mind what to do next, but sometimes it doesn't, so it chooses something from the pool.
Yeah, tell me about that time. So what could be the condition for that time?
Maybe a process that will come next is terminated unexpectedly for an error.
Well, in that case, it is like a process exit, either voluntarily or involuntarily. That's a process exit. We are talking about the interrupts, timer interrupts. Okay.
What if the process I'm going to get to is blocked because it's waiting on a semaphore on mutex?
Well, it is. If it is blocked, okay, it is like a fork. It's a system call. Okay. We are talking about the timer interrupt, and we already have a condition if a process blocks. What is sometimes after timer interrupt? What is timer interrupt? Timer interrupt happens 20 times or 50 times a second. Okay, there is a I/O device which is called clock, system clock. It causes an interrupt 50 times a second. Okay, 50 times every second it causes an interrupt. An interrupt is handled by the operating system, of course. After each interrupt is handled, sometimes the scheduler make a decision, okay, I am going to make a new scheduling decision now. What is that sometimes? If the scheduler thinks that the current process used too much CPU time, its time is up, maybe I should switch this one. Okay, the process is runnable, it needs all the data that it needs to run, it doesn't need any operating system help, it likes to use the CPU, but the scheduler thinks that time is up. Okay, so after the timer interrupt, the scheduler comes in and scheduler says that I am going to put this process in the ready queue, and I am going to make a scheduling decision, and somebody is going to run. Somebody else is going to run. So that's what sometimes is. Not every after timer interrupt there is a scheduling decision. Okay, but in after some timer interrupt there is a scheduling decision. So you might say that what is good the timer interrupt then? What is good? Why do we use the timer interrupts then? I mean, if there are no scheduling decisions after each timer interrupt, why are we doing this? But there are many bookkeeping operations that the operating system do at every timer interrupt, and we are going to see it when we talk about the when we talk about the when we talk about the memory management, and when we talk about the scheduling and all that kind of other stuff. Okay, good. So related to timer interrupt is preemptive and non-preemptive schedulers. Okay, there are preemptive schedulers and there are non-preemptive schedulers. Okay, non-preemptive scheduling is this: you let a process run as long as it wants. Okay, when a process starts, as long as it wants, it uses the CPU. It is only switched if that process blocks. What do we mean by block? That process wants the operating system help. It asks the operating system to provide some data from the network. I need this data from the network. It is not available. So operating system says that, okay, you are blocked. I don't have that data. I will wake you up. I will unblock you when the data is ready. Now you are on the block list and you are waiting for your data, and I'm going to switch. So for the non-preemptive scheduler, okay, the process runs as much as it wants. Okay, if it doesn't need any help from the operating system. That's the non-preemptive scheduler. On the other hand, for the preemptive schedulers, operating system says that, okay, if you are a CPU bound process, you could use the CPU for at most maybe 50 milliseconds. After 50 milliseconds, okay, when the timer interrupt comes, I'm going to switch. So each process is assigned a quantum time, and quantum times are usually 50 milliseconds, 20 milliseconds, and etc. Okay, when the CPU when the scheduler realizes that the current process used, more than the quantum time, then the switching happens. That's called the preemptive scheduling. And most of the modern operating systems are preemptive operating systems. They preemptively switch between processes if the quantum time is up. Okay. Of course, for the preemptive scheduling to happen, I definitely need the system clock. There should be a system clock, and that system clock should be causing interrupts at regular intervals. Okay. If there is no clock available, okay, non-preemptive scheduling is the only option. Okay, so there should be a clock, system clock, and that system clock should be causing interrupts, and interrupts should be handled by the operating system. Okay, so clock is important. Sure.
Can we say that non-preemptive scheduler is not fair for processes?
Well, I wouldn't say that. Depending on your operating system. If all the processes are CPU bound, okay, when they get their CPU time, they use the CPU as much as they want, and one way or the other they need some data from the operating system, so they will be blocked, and all the others are using the CPU the same way. Then you will say that they are fair because everybody is using in a given minute. If I have 5 processes in a given minute, if each of them is using 12 seconds of CPU time, then I would say it is fair because they are all behaving the same. But if some of the processes are CPU bound and some of them are IO bound, then yes, you cannot be fair in these kind of cases because one of the processes will take the CPU in a very short amount of time. It will need the data. It will be blocked. Once it is blocked, another process will take the CPU, which will be the CPU bound process, and it's going to use it. So that will not be fair. Okay. So again, it depends on your operating system. If you are in an interactive operating system like the Windows desktop Windows or the Ubuntu that we are using, you cannot imagine that you can design such systems without the help from the clock. So they all have to be preemptive. If it is interactive, then you have to be preemptive. Otherwise, you will have very angry end users. I mean, they have to wait for somebody. They will have to wait for very lengthy process to complete this job, just to get the mouse click result. So that's not going to be good. But for batch systems, preemption is not that important. By the way, what do you think? Are real-time systems preemptive or not?
Non-preemptive?
Are real-time systems preemptive or not preemptive?
Wait, they are preemptive because they have a clock since they switch every like 20 milliseconds, you said?
Any other guesses? Any other guesses?
Don't we have provide the time for processes, so it's not totally non-preemptive or preemptive, I guess.
They are non-preemptive. Okay. Well, they have the clock. The fact that you have a clock doesn't mean that you have to preemptive. They have the clock, of course. Okay, they use it for different reasons, but they are not preemptive because each process is designed in a real-time system. Whatever it needs, where is my real-time system? Where did I draw it? Oh, okay, here it is. Okay. Each process in the hard real-time systems, each process is assigned a certain amount of time, 25 milliseconds. This process A has to complete its job in 25 milliseconds. It is the task of the process. Okay, you might say that what if I have a bad process and doing this and this and this and this? Well, then you didn't design your system very right. So real-time operating systems, hard real-time operating systems are non-preemptive. It is a task of the process to complete whatever it needs in 25 milliseconds. For the soft real-time systems, and we are going to see the differences later, the things might be different. Okay.
Sir, this time interval you said, for instance, 25 milliseconds, doesn't it change with every software update, a big software update or upgrade, for instance, Windows 7 versus Windows 10 or Linux 18 versus Linux 20?
We are going to see it's not a fixed time. It changes from process to process. And you can change it too. Okay? You can change it too. I mean, you may lower it, upper it, and you can change that kind of parameters if you are the administrator. But depending on your interactivity, depending on your process type, okay, quantum time changes. Usually, okay, question again. Let's say you have priorities for your processes, okay? You have priorities for your processes. You know that high priority processes are run first. If they are ready, they have to run. Okay, would you assign low quantum times for the high priority processes or high quantum times? Let's say I have two process types, high priorities and low priorities. Would you assign a quantum time of 10 milliseconds, 20 milliseconds for low and high, or 10 or 10, or 20 or 10? Which one? A, B, C. Which one would you choose? High priority, low quantum time, low priority, high quantum time, or equal, or just opposite?
High priority, high quantum time, I think it's more suitable. So
C, you mean C, right?
Yeah.
Any other guesses?
Logically speaking, it sounds like C, but my gut says that it's probably A.
So, Usama, how many classes did you take from me?
This is my third, second.
Yeah. So when did you understand that if I ask him a question, it's a trick question all the time? So you know me now.
That's what I'm saying. Like.
Yeah. Okay. Yeah. So, but you want to say C, but the way I ask is not C, right?
Right.
Yeah. The answer is A. For the high priority jobs, you assign low quantum times. Why? Because if you have more than one high priority job, okay, you like to switch between them quickly because they are probably interactive processes, right? So switch quickly between them so that they are interactive, they are lively. They just respond in a short amount of time, okay? So why don't we do the same thing? Why don't we choose quantum time small for all the processes so that they switch quickly, so they keep responding? Why don't we do that? What is the downside of having a small quantum time versus large quantum time? So what is good with the small quantum time?
So it may cause too much interruption.
So what is bad with interruption? I mean, I don't feel like I'm interrupted.
For the sake of the efficiency, CPU usage efficiency, I think too much interruption.
Too much interruption means context switch, right? And context switch is expensive.
Yes.
Okay,
yes,
so lower quantum times, smaller quantum times means that there will be lots of switching. Lots of switching is good for interactivity, responsiveness, but you are going to spend 20% of your CPU time, system time for context switching. That's not efficient. That's why I like to keep my quantum time as long as possible. But longer quantum times means that my processes will behave sluggishly and people won't like it. The end users won't like it, especially for the interactive programs. So assign high, large, long, whatever quantum times for the low priority tasks. Probably they are backup processes, okay, some watchdog processes, some bookkeeping processes which don't need interactivity. Once they start running, don't let them switch. Let them run as much as possible. The fact that they are running means that there are no high priority jobs available. There are not high priority jobs in the ready queue, right? That's why the low priority is running. That's why I would use this A part, okay? Lower priority for the uh, lower priority jobs get the higher quantum time. So these kind of decisions are actually looks complicated, but people have learned it with the experience, and people have made decisions on them. And these are part of the operating system. The question started from this. Somebody asked, I don't know who, I think Mohammed asked this. I don't know. Does the quantum time change from one release of the operating system to the next? Okay. Well, I mean, we don't have to wait for the operating system release. Quantum time changes from process type to process type. Okay. So it is the part of the operating system design, and it depends on the interactivity of the process. It depends on the priority of the process. It depends on the CPU switching and etc.
Did I get this right, sir? In the same program, there can be different time intervals, right? With different processes.
In the same, you mean in the same process? If there is a single process.
Same program doing different processes.
Yeah, if you have more than one process running for you, you can change the priorities of it. Once you change the priorities, the operating system might decide that lower priorities will have higher quantum time.
Okay, thank you.
Okay. Do you know how to change your priorities, your system priorities? You go there, and I think you find it. I always forget about this. It is somewhere, maybe in the details. Yeah, so these are all, look at this. These are all running. I think they are ready. Can I do this? Okay, so it is using this much of the CPU time. I think somewhere around here, you may see the priority of it, or maybe let me go to my fake Unix. Okay, when I say PS, show me all the, okay, so priority is 20, see? My priority is 20. If I like to lower my priority of process, I would say I am going to be nice. Okay, I'm lowering my priority. So if there are other processes running, I will keep my priority low. When I say nice ls and maybe ALRT starting from the root, but this is going to, okay, and let me do this way, so that, where is my ampersand? Find ampersand for me. Yeah, here it is. I found it. So it is running in the background. When I do this, where is my priority? So the priority for the ls is 10 now. See, it is 10. It is different. It is, oh, okay, let me shut this up. It is lower than the other one. For Unix, actually, Higher the number priority, higher the number, lower the priority. But this is a fake Unix. This is using the Windows priorities. Okay, so I can change my priorities. I lowered it. Usually the regular users are not allowed to increase their priorities but lower it. That's why it's called nice. There is an option to use nice with a negative number. Then in that case, you are increasing your priority, but you are not allowed to use it if you are not the super user. Okay, these are all depends on the system that you are using. Okay, good. So let's look at the real scheduling algorithms actually, and we are going to look at them by their category. It is batch systems, interactive systems, and real-time systems. And as I said before, real-time systems are often non-preemptive. They don't need to be preemptive. I mean, if somebody designed a real-time operating system and it needs to be preemptiveness, then things are going to go wrong because if you can't fit into the, I mean, what kind of processes would I run on an operating system, real-time operating system? Okay, let's say in a 1 second interval, I have divided this into slots. A is running, B is running, C is running, then A, then B, maybe then A again. This is the design in a single second. Okay. If A cannot complete its job within this milliseconds, okay, within this, let's say 100 milliseconds or 200 milliseconds, then that means that A is not done. What might be A doing? A is maybe measuring the temperature of the nuclear power plant core, okay? So if A is not done measuring the temperature of the nuclear power plant core, that means that my nuclear plant is going to blow up in a few minutes. That's not good, okay? If I gave A 200 milliseconds to measure the nuclear power plant core temperatures and take the necessary action to cool it down, if it cannot complete its job in 200 milliseconds, that things are not going well, okay? So they have to fit into this 200 milliseconds. You cannot take the CPU and if I am going to preempt you, then this is not a real-time system. We will come back to this. Let's start from the batch, okay? But before looking at those specific batch, real-time, or interactive systems, all three of them, okay, the goals is the same: fairness, okay, give each process its share of the CPU. And we didn't say the equal share of the CPU. Some of them, as the priorities say, okay, some of them has to have the more priority, some of them have lower priority. So fairness means that whatever I have promised, I should do that. That's the policy and enforcement, okay? Give preference to work that is administratively favored, okay? So if I have priorities and if I said I have high priority, low priority, and middle priority processes, if I have high priority processes, they should definitely run. If I don't have any, then middle priorities and low priority processes, okay? And I should never let a low priority run while H is ready, okay? And remember inversion of priorities, priority inversion with the spin locks, we talked about it, right? So don't let that happen, okay? Prevent subversion of OS scheduling policy. Always keep your policy and be careful about this. And balance is keep all parts of the system busy. When we talk about CPU efficiency, we always said that we shouldn't keep the CPU idle. But we should be careful about keeping all the other parts of the system busy too. For example, if one process wants to get the data from the hard drive, let that process run first, ask the hard drive to load the data. While the hard drive is working on that task, let another process run. So you are keeping both of your hard drive and the CPU busy. So this is more efficient. Okay, so fairness, policy and enforcement and balance is always the things that we are going to look at. Okay, let's look at the batch systems. Batch systems, we don't have the interactive. What's a good example for a batch system? Banking applications, for example, or the airline reservations, or the, for example, the telecom operators. The Türk Telecom, for example, has to process millions of invoices every month, and you run them in your batch system mainframe computer, and you know that running all those invoices will take you maybe 5 hours of work. Okay, so there is no interactivity. It keeps getting the user data, it adds all the numbers, does the multiplication, add the tax, and etc., and it produces all those invoices to send to the customers. So there is no interactivity, as I said, and one process runs after the other one, and approximately I know how much time it's going to take. Okay, so the goal for the batch systems is throughput. Okay, how many jobs I complete per hour. The turnaround time is important. When I assign a job, when I say calculate the invoices first, for the Türk Telecom, calculate the invoices, prepare the invoices, and prepare my payroll. Okay, because I have thousands of people working for me, I need to pay them. Also, prepare my taxes. Okay, three processes: invoices, payrolls, and the taxes, A, B, C. Okay, if I submit this job, how long would it take you to finish it? That's the turnaround time. Okay, and of course CPU utilization is important, because I am running this on a very expensive computer, and I like to keep it busy, because most of the time I rent those kind of computers either physically or either on the cloud. For that kind of CPU, I pay maybe $1,000 per hour, whatever. Okay, so throughput, turnaround time, and CPU utilization are the things that we are going to be careful. As you see, we don't talk about interactivity here. We don't talk about responsiveness. Maybe the turnaround is kind of responsiveness. If I submit this task, if I submit this payroll job, how long will it take you to complete? Well, that's the turnaround time, right? It is not exactly as interactivity, but I like to know how long it would take you to finish this one. Okay, so we are going to look at them one by one. Then we have the interactive systems. Response time is important. When I hit a button, okay, people usually have their expectations. Okay, people usually have their expectations, and their expectations depends on the human psychology, because we are all humans. Okay, we don't behave the way the computer scientists or the operating system designers want us to behave. Okay, we have our behavior. For example, the experiments did this. The users have a sense of cheap and expensive requests. Okay, by cheap I mean this. If you see my mouse, right? If I do this, if I click and do this dragging, I expect to see this line immediately, because drawing something on the screen is so cheap. It has to be done now. Okay, I know that. That's a cheap expectation, and it has to be done in a fast way. I mean, as a human, I think it that way. It might be very complicated for the computer to do it, but as a human, I expect it very short amount of time. Okay, but if I like to open a file, if I do this, and if I like to double click on this file, and I know that it's going to take maybe 10 seconds to open this file, and as a human, I think that that's expensive. I can tolerate waiting for 10 seconds for that file to open. But when I click on an OK button, I immediately see the result. I like to immediately see the results. That's the human psychology. And human psychology doesn't correspond to the reality in computer science or computer engineering. When I click OK button, sometimes the processes that I do with the OK button is so much it's going to take a long amount of time. And sometimes drawing those lines when I make this click is going to take lots of processing, and it's going to be expensive really. So we have to be careful about this psychological factor when we are dealing with the interactive systems. Interactive systems. Okay, the systems, the user interfaces that understand the human psychology are more successful systems. Even though they are running on the same hardware, they are carefully designed, so humans tolerate those kind of behavior. For example, when I click something and I see an hourglass, there is an hourglass. Like, how do you draw an hourglass? Is this a good hourglass? So there is this sand flowing down here. Okay. When I see the hourglass, I know that computer is doing something, and I can tolerate this. But if I don't see anything, I click the OK button and nothing is happening. So I would think that the program is crashed. Maybe I didn't click it right, and etc. So interfaces, operating systems giving these kind of feedback to the users are more successful, and they are more compatible with the human psychology. For the real-time systems, the main motivation is meeting deadlines. Okay, meet the deadlines. It has to be all predictive. Okay, if process I runs, I know that it has to finish in 25 milliseconds. If not, then I will be in trouble. Okay, I will be in trouble. My ABS brake on my car will not work, or my control algorithms with the nuclear power plant will be doomed, and etc. Very bad, very bad results. Okay, meet the deadlines. It has to be predictive. I don't know how long it's going to take. No, you cannot say that. Okay, and requires careful engineering to match the priorities to actual completion times and available resources. Okay, that's why most of the time hard real-time systems say that you cannot add a mechanical hard drive to the system, or you cannot add a regular hard drive to the system. Okay, if you are going to add it, it has to be special, this kind of drive, or no drives at all. Everything has to be in the memory. Sometimes very limited systems. Good. Okay, so let's go back and let's start again from the batch schedulers. Three main scheduling algorithms. Okay, remember, with the batch schedulers, throughput is important, job completion time is important, right, and CPU efficiency. Those are the three things. Also, for the general scheduling algorithms, we have to be fair, right, and we need to keep the all parts of the system busy. Also, we need to enforce the policy. Okay, so let's look at this first come first served, but it looks like I am out of time for the first part of the lecture. Let me take questions if you have any before I take a break.
Sir, I have a question.
Sure.
What is the difference between binary semaphore and mutex?
Oh, you don't. Your question is about the interprocess communication. They are exactly the same.
Yes.
They are exactly the same. Binary semaphore and mutex are exactly the same. We call binary semaphores mutexes.
All right, sir. Thank you.
Any other questions? Good. Okay, let's take 10 minutes of break. Let's be here 12:33. So let's look at these three batch schedulers. First come, first served, as the name implies. Whoever comes first will be given the CPU first, and we will wait until it is done. Then we will continue. Okay, run the first process on the run queue. Okay, when the running process blocks, the first process on the queue is run next, etc. And there is no preemption. Preemption is good for the interactivity. For the batch systems, we don't have interactivity. Okay, and if we don't need it, preemption is going to be expensive. It's not needed, because for the preemption I need the clock timer. Every time the timer happened, I need to switch, and if I need to switch between the processes, that's going to be expensive. So there is no preemption based on the timer, and it is very simple. Okay, it's just like waiting in the line. Of course it is not very fair. Okay, because we don't try to it's like waiting in the line again. I mean, let's say three people are waiting in the line. The people in front of the queue is handled, but if he has to come back again, he has to wait the whole line again. If one of the customers is handled for a single, the first time comes to the clerk, bank clerk for example, then he gets to go, but the others has to wait the same line over and over again. So this is not very fair. But as we said before, we are not looking at the fairness with the batch systems. The important thing with the batch systems is the CPU utilization, or the system utilization. So if you are talking about the fairness, you have to do some other stuff. Okay, another we said that CPU utilization is important. Okay, for the batch systems, but throughput and turnaround time is important too. What is throughput? Throughput is maximize jobs per hour. Okay, how many jobs you completed. For example, let's do this. Process A, I know, is going to take 20 minutes. Process B is going to take 10 minutes, and process C is going to take 30 minutes. Okay, doesn't matter which one I run first. All three of them totally will take 60 minutes of time. So throughput will be, okay, 3 over hour. So three jobs per hour. That's the throughput. Turnaround time, I mean, it doesn't matter if A is first or B or C, but turnaround time, okay, is going to be different. Turnaround time is going to be different. If I run A, B, C, or A, C, B, or C, A, B, you know this, right? Okay, C, B, A, and B, A, C, and B, C, A. Turnaround time is going to be different for each of them. Why? Because in this case, A is going to be completed in 20 minutes. Okay, so it is 20 minutes, plus B is completed in 30 minutes, plus C is going to be completed in 60 minutes. If I divide them by 3, it's going to be what? 81. So it is going to be and 3, right? So it's going to be 36 minutes per 36 minutes per process. Okay, so which one is the smallest turnaround time? Which order is the smallest turnaround time? I think this one is over 3, right? How about this one, ACB? ACB, for the ACB is going to be, let's do it this way, okay. For ACB is going to be 20 plus C is 50 and B is 60. So it is over 3. So it is 130 over 3. So definitely ABC is better. So which one is the better choice for the turnaround time? Throughput is the same. How about the turnaround time? Which one? It is better to run the smaller processes, faster processes first, or larger processes first?
Larger is better, I suppose.
Smaller, CAD.
CAB, you guys are saying run the C first, then A,
Yes.
then B. Then in that case it's going to be 30 plus 50 plus 60. Is that, am I doing it correctly?
No, BAC, sir. I think that's the best.
BAC. So what is this? 30, 90 plus, so 130. Again, 130 over 3. And you are saying what? BAC?
Yes, BAC.
10 plus 20, no, 30, right? 10 plus 30 plus 60, right? So it is 100 over 3. So I think BAC is better for the throughput. 100 over 3. So the idea is run the fastest process first for the throughput. Okay. Where is my, okay. That's the idea, shortest first algorithm. Okay. It is probably optimal turnaround time. If I have A, B, C, D, A is 8, B is 4, C is 4, and D is 4. Okay. Doing it this way, B, C, D, A is the best. Why? Because D contributes less to the mean. D contribute, okay, less to the mean when I do it that way. So 4A plus 3B plus 2C plus D over 4 is the best. So if I just change it, okay, if I change the order, I will have to, these all have to wait until A is done, right? So A is the slowest. B and C and D has to wait the slow process to finish. So their times will increase. So they will contribute more to the overall throughput. But if I do it first, A has to wait the short processes, and the short ones will quickly be done, and they will contribute less. Okay, they will contribute less. So it is probably optimal turnaround time with the shortest first. So how do I know that process is going to take 8 seconds and B is going to take 4 seconds? How do I know that before running them? Can you calculate how much a process is going to take on your computer before running the process?
No, so
No, you can't, right? So how do I know
it,
A is going to take 8 seconds then? Yeah, exactly. So I would run them because these are batch processes. There are no original batch processes. If I am calculating the payroll, okay, or if I am calculating my taxes or my invoices, I know I have 10 million customers, okay. For 10 million customers, it's going to take 3 hours. I know that because I did that last month, okay. So for the batch processes, having this kind of information is available. So I can guess which one is going to be faster, shorter. Okay, so this will increase the, again, shortest first is probably optimal turnaround time. Okay, again, the throughput is going to be the same because I have to wait I have to wait 16, 20 seconds for all of them. Whatever order you choose, doesn't matter. So when you do that, it's going to take 20 seconds, but jobs per hour, jobs per second is going to be lower if you do the shortest first. Okay. Of course, this assumes that before I do the scheduling, I have all the processes available. They submitted A, B, C, D at the same time. I know their names. I know how long they are going to take. But this is not always available. Okay, this is not always available. Let's look at this one. We say that jobs don't arrive at the same time. Okay, let's say I have 1, 2, 3, 4, 5 jobs. A is going to take 2 seconds, B 4, C, D, and E will take 1 second each. But their arrival time is different. Okay, their arrival time is different. So process A and process B arrived at time T0 at the beginning. While I am running these, okay, process C, D, and E arrived at time 3. Okay, so if I run B, C, D, E, A, average wait is 4.4 seconds. Okay, so run B, then C, then, because if I run D, it will take 4 seconds. After 4 seconds, I see that C, D, E arrived. Okay, now I can say that, okay, C is shorter, I am running it. Okay, so it's going to take 4.4 seconds. But if I didn't know that there is a shorter process is coming, my decision would be run A first. After A is finished in the second, number 2, I have only B. I am running B now. When I started running B, it's going to be 6 seconds before I see that C, D, and E is available now. So to be optimal, to make this optimal, you need to see into the future, but this is not available, right? This is not available. So if you are doing the pure batch processing, let one process finish before the others start. This is the best we can do, shortest first. Okay, I don't know. I don't know which one is going to come next while I am running something. Okay, or we can do something else. Maybe can you tell me what we can do to solve this problem? I am running A first. A is going to take 2 seconds. And after that I started running B. B is going to take 4 seconds. But while I am running B, I received C, D, and E. They are all short. So I like to run the short jobs first. But I am running B. And I have to wait until B is done. So let's make a change in our scheduling algorithm. Instead of running shortest running time first, maybe we should run a scheduler that does shortest remaining time next. Okay, it's like preemptive, but it is not preemptive. That depends on the quantum time. It is preemptive that depends on the remaining time. Okay, so whenever I receive a new job, I calculate the remaining running times of all the processes. If there are shorter processes, then I will let them run. Okay, so it is a preemptive variant of first come first served. I need to know the run times in advance. Here I am running A, then I started running B. While I am running B for 1 second, I received C, D, and E. I know that B needs 3 more seconds. So the picture is this. B is 3, C, D, and E, they all are 1, 1, 1. So what do? I switch. I switch from B to C, then D, then E, then B again. Okay, so that will increase my throughput and I will get the optimality. But again, so what is the cost? The cost is more complicated system. I am stopping a running process and I am letting the others do the running. Okay, so this is called shortest remaining time next. First come first served. Okay, this is very simple, but this doesn't care about the throughput time. Okay, or turnaround time. If we like to optimize the turnaround time, okay, if we like to optimize the turnaround, sorry, at the beginning, first come first served, it doesn't care about anything. It's very simple, no preemption. Whoever comes in, I will start running it. But if you like to optimize the turnaround time, shortest first is good. But the problem with the shortest first is we don't have all the jobs available at the beginning. The jobs arrive while I'm running something, right? So I invented this shortest remaining time. Okay, so this requires preemption based on the amount of time, duration of the time remaining for the processes. Okay, can you guys explain me this? May have a problem with indefinite overtaking. What is this? This is about fairness. So shortest remaining time has this problem. The others don't have this problem. The others don't have problem, but shortest remaining time has the problem. So
if short tasks keep coming in, one long task that we were supposed to start at the beginning may not start executing.
yeah, while I am running B, D, C, D, and E arrive. They are all 1 seconds. So I push B at the end of the queue. I run the C, D, and E. But if I still keep receiving new jobs that are all shorter than B, B is not going to be run for a long time. And if I keep those kind of jobs coming all the time, B will never run. So that's called indefinite overtaking. And sometimes we call this starvation. Okay. B is starving. Okay. B cannot get any CPU time. That's not a good thing. That's not a good thing with the shortest remaining time next. Okay, and we are going to see this problem over and over again. For now, we don't have a solution now. Of course, we can suggest something, but we will see some solutions for this problem later.
So,
Good, yes.
how does scheduler get those kind of timing information from the process table or thread tables? I mean, remaining time or arriving time is okay, but remaining time. How does scheduler knows about the remaining time?
Well,
Does it predict it or?
as you as you said, so how do we know that a process is going to take 8 seconds or 4 seconds or 4 seconds? I think you said that it
Yeah.
is the experience, it is the statistics that we had about that process previously. But how would I know that I have run this process for a second and it needs 3 more seconds? Of course, these are process tables, right? And in process tables, what do I keep? The statistics about the processes. Remember this one? Okay. Remember this one? For each process, when I look at the history, okay, they all have their CPU times, how much CPU
Okay.
they have used. And if I know that this process needs 30 more seconds, right? So total time is 50 seconds. It used only 20 seconds. So it needs 30 more seconds. And these kind of statistics are all kept in the process table. Okay, good. Any other questions? Okay, so the starvation is important, and we will talk about this over and over again. It will come again. These numbers, I think I showed you before. I have shown you these before, and just compare some common tasks that we do with the computers. Okay, 1 nanosecond. Okay, we have nanoseconds. We have microseconds. Couldn't write micro. Okay, microseconds, and we have milliseconds, right? So this is -3, -6, and -9 seconds. Okay, so L1 cache reference is 0.5 nanoseconds, very, very fast. Okay, L2 cache reference is 7 nanoseconds, and this is how much it takes for you to lock a mutex. 25 nanoseconds, pretty fast. Of course, I am assuming that one bit of mutex variable, global variable, is in my cache, right? So if it is in the cache, then locking it, unlocking it using the TSL instructions is fast. But I need to execute that loop. You remember that loop, right? Okay. Main memory reference is very, very long compared to, okay, compared to accessing your L1 cache. Okay, so it is L1 cache reference is half a nanosecond. This one is 200 times slower. Okay, so when I say we need to invalidate the cache when you do the context switch, and you need to reload the cache, you know the cost, right? Okay, repopulating the cache when you do the context switching, L1 cache, L2 cache, is very expensive. Because you need to load all that data to the cache, and if you have dirty pages in your cache, you need to write them to your memory. Okay, so this is 1 microsecond. Some algorithms compressing 1 kilobyte of data is going to take 3 microseconds, and reading 1 gigabyte of data from SSD is going to take 150 microseconds. Okay, so it is expensive. We are talking about not nanoseconds but microseconds. Okay, SSD random read. Sorry. Just read the minimal amount of data from SSD. Okay, it's going to take 150 microseconds. So reading from the memory is how many times? 1,500 times faster reading from the main memory. Although this is a solid state, their technologies are different, and you need to go through the bus. If I like to read data, okay, from the disk, is going to be very expensive. Only making a disk seek, moving your disk head from one position to another one, on the average is going to take 10 milliseconds. Here we are talking about 150 microseconds. This is 10 milliseconds. Okay, this is 1000 times or 700 times more expensive. Okay, so these are the numbers that we need to be careful of. So the idea is, don't read anything from the disk. Okay, if you need to read some data from some external device, read it from SSD. But SSD is so slow too. If you can get away with it, read it from the main memory. But if you can do it, always start with the cache. Don't do context switching. Context switching is very expensive because you need to go to main memory. The worst thing is if the data that you are looking at is not in the main memory, then you have to load it from disk. When we see the memory optimization next chapter, memory management, because not all the memory data you need will be in the memory. Then you have to go to your SSD or the hard drive. That will be very expensive. Those page faults will be very expensive. That's why context switching is so expensive. Good. So keep these numbers in mind. This is just a simple visualization, of course. And when we refer to numbers, and maybe we will come to this, print this out on a color page and hang this on your wall or your drawing table or whatever, or memorize it, better yet. Okay, so let's look at the interactive systems. As you see, we have many options with the interactive systems because there are many parameters with the interactive systems. Okay, the simplest one, like the first come first served. Then we have the priorities. Okay, and the analogy between the interactive systems and the batch systems, shortest process next. And there are some simple but efficient scheduling techniques, such as guaranteed scheduling, lottery scheduling, or fair share scheduling. Let's look at them one by one. Round robin scheduling. It is this. Okay, the simplest scheduling, the oldest one. You put your processes in a queue, circular queue. Okay, I am running B. When B is blocked, next process F will be handled. Or I am done with B. B is blocked, or it is preempted, whatever. Okay, so I put F at the beginning of the queue and B is at the end, and it does this in a continuous loop. This is called round robin. Okay, why is it round robin? Because it's like dönme dolap in Turkish, right? Dönme dolap in Turkish. So these are my processes. Okay, they are rotating this way, and I keep running this one. So they rotate around this point, about that axis, and this is called round robin scheduling for the interactive processes. It's like first come first served kind of thing, but since I know that there will be lots of blocking and there will be lots of preemption, okay, when B is blocked or preempted, if it is preempted, then I will put it at the end of the queue. If it is blocked, I will put it at the end of the blocked queue. So it is the simplest, fairest, okay, most widely used algorithms is round robin, one of them. We like it because it is easy to talk about for educational purposes. It is very simple, and it is kind of fair too. Okay, it's kind of fair too. I wouldn't say that it is the fairest one because it doesn't make any distinction between I/O bound processes and the CPU bound processes, but it is good enough for most of the cases. Okay, maybe I can adjust this fairness with the time intervals or the quantum time. Okay, so give more quantum time to, or give, no, sorry, maybe I can adjust it using the priorities. Give more priority to give more priority to I/O bound processes so that they have more chance of running first. Is this a good statement? Giving more quantum time to I/O bound processes doesn't make any difference. Am I saying something correct? If I give more quantum time to interactive processes or I/O bound processes, they will use the CPU more. Is this correct?
No, it's not correct because they will always wait for the I/O.
Yeah. If I tell them that, okay, you have your quantum time of 100 milliseconds, well, they will be blocked. They will be blocked in their first 20 milliseconds because they need some data from the hard drive. So increasing their quantum time doesn't do much for them because they will be blocked anyway. So it is better for them to have a higher priority than the CPU time, CPU bound processes. Okay, good. So round robin scheduling with preemption based on the time. Round robin scheduling with the preemption based on the time is one of the simplest and oldest ones. Okay, but how much quantum time should I assign? Is there some kind of a trade-off? Longer quantum times means that efficient, no context switching, unnecessary context switching, and we like it for the CPU usage. You remember how much it costs to go to the memory, invalidate the cache, and repopulate it. Okay, longer quantum times we like it for the CPU case, but longer quantum times are bad for the interactivity. Okay, so shorter the quantum, the more responsive the system. We know this. But shorter the quantum, less CPU utilization. We know this too. Okay, so there should be a balance. No, not very short, not very long. Okay, suppose the computer quantum is 4 milliseconds. Okay, and the process switches take 1 millisecond. Okay, so that means that 20% of your time, CPU time, system time, is going to be wasted for context switching. Okay, and if we have 100 millisecond quanta, and after 100 milliseconds we have 1 millisecond of context switching, that means that I am wasting only about 1% of the CPU time for context switching. Okay, but 100 milliseconds, that means that if I am running 20 interactive processes, okay, 20 interactive processes, and if I use 100 milliseconds for each process, that means that on the average I will have to wait 1 second, okay, to get a response from an interactive system. People won't tolerate this. They will not be happy. So I need to find a balance. So maybe 20 milliseconds, 50 milliseconds is a good quantum time, right? Maybe 20 or 50 milliseconds is a good quantum time. You might say that for a cell phone like this, okay, for a cell phone like this, I have the CPU, I have 8 core CPUs on this one. I am not using most of the CPUs, right? So maybe let's keep the quantum time small so that my cell phone stays very, very responsive. That might look like a good idea, but again, you are using the CPU time. Using CPU time means that you are using your energy, battery time. And for the cell phones, interactivity is important, but battery time, energy amount is important too. So I cannot keep my quantum times very, very small, because instead of spending 100 watts per hour, if I keep my quantum time very, very small, I'm going to spend 120 watts per hour, etc. Okay, so quantum length is directly related to interactivity and the CPU and the battery usage. So are there any formulas for good quantum times? Well, it looks like no. It is based on user experience, right? If the humans are involved, doing the experimentation is very difficult, because there is no standard human. Okay, you need to let them use your system and get their opinions and take the means and eliminate the outliers and etc. Do the experimentation again. What are my target user profile? Are they university students? Are they illiterate people? Are they young people, old people, etc.? For the cell phones, everybody. Okay, for the cell phones, everybody. So developing those kind of systems is not that easy. Okay, so what did I say? If the process is interactive, then our quantum times should not be very, very long. But if the processes are not interactive, why should I make it 20 or 50 milliseconds? I will keep their quantum times very, very long. Since there is no interactivity, it will be good for me to have less switching counts. So there is priority scheduling. I will have classes of processes. High priority processes, okay, they will be the interactive processes or the system processes. Their quantum times will be very small. So between themselves, there is lots of switching going on. I am going to waste some CPU time, but that's what it is. I will have to take that cost. Okay, I will have to take that hit. But for the low priority tasks, I don't have to take the hit. Keep the quantum time larger. Okay, keep the quantum time larger. So what I'm gonna do is I will do the priority scheduling. I will keep 2 round robins or 3 round robins. Okay, it's like high priority queue. These are the processes for the high priority. Okay, in the middle I have these. For the low priority I have only 2 maybe. Okay, I don't run middle or low level priorities while there is high level priority available, runnable. Okay, but again, I have to be very careful about this priority inversion. Remember, we should be careful about the subversion of the system policies. It is this point. Okay, let's look at this priority inversion. We did this before. Okay, consider these 3 processes: high priority, middle level priority, and low priority. Okay, so this is the scenario. H needs a lock currently held by L, so H blocks. H needs a mutex and it cannot get the mutex, it is blocked. Process L, which has the lowest priority, holds the lock. It is in the critical section. Okay, and if I have M runnable, if I have M runnable, M will keep running because it has a higher priority than L. That means that L has to wait until M is done, but H is waiting for L to leave the critical region. So in an effect, H is waiting for M to finish. So that's called the inversion of priorities. And in this case, M is behaving like it has a higher priority than H. So H is indirectly waits for M. Okay, we don't call this deadlock because there is no deadlock. Eventually, M will be done. Either it will be blocked or will be preempted. No, it is not preempted. It will be blocked because preemption means that if M is preempted, it is still ready to run. It will keep running, right? So M has to be blocked. When M is blocked, if there are no high priority jobs, then the low priority job will run L, and L will release the lock. As soon as it releases the lock, H will start running. Okay, so that's not a good thing. That's not a good thing. And this kind of stuff happened on real operating systems. One interesting case was on the Pathfinder, which is one of the Mars missions, like 15 years ago maybe. Luckily, this problem happened while they are transferring the robot from Earth to Mars. As you know, there is a very large distance between Earth and Mars. The travel takes months. Okay, by the end of the travel, in the last 2 or 3 weeks maybe, they have realized that the computer keeps booting up because there is a watchdog timer. Notice that H is not running. Okay, there is an important process, it is not running, and they don't know why it is not running. Okay, so luckily there was a watchdog timer. Watchdog timer says that, okay, I know that H has to run, but it is not running, so I am going to reboot the whole system. It reboots the whole system, but H is not running still. So the reason why H is not running, because there is a low priority job. I think it was taking a backup. I think it was taking a backup or something. That backing up process, since it has a low priority task, it doesn't run either. So H is waiting for that low priority job to finish. So it is the priority inversion problem. So they find it on an exact copy of the computer on Earth, and they solved it. And Pathfinder served the science community for a long time. Okay, so this happens. Priority inversion is not something theoretical. It happens. So when you make a decision about the scheduling, this kind of important stuff, sometimes you may never know what the real results will be. Okay, I mean the question that I ask you, many questions: should I assign a longer quanta or lower quanta, higher priority, lower priority, etc. It is not easy to guess at the beginning. You need to have some experience first.
So I couldn't understand how does M get the term after the L before the H gets one. H couldn't get the term, but M, how does M get the term?
Let's say this, okay? I have high priority task P1, middle priority task P2, and P3 is the low priority task. P1 is running, okay? P2 is ready, P3 is ready, but P1 is running because P1 has the higher priority, okay? P1 is running and P1 needs a mutex to enter a critical region, okay? So it blocks. Mutex is not available. P1 blocks, okay? Who holds the mutex? By luck, this P3 holds the mutex. Okay, so P3 has to leave the critical region to release the mutex. So P3 has to run. But since P2 is available to run, it is runnable. previously couldn't run because P1 was running. P2 takes the CPU and it is running. So in effect, this means that in order for P1 to run, P2 has to finish, so that when P2 finishes, P3 can leave the critical region. So in effect, P1 is waiting for P2 to finish, even though it has a higher priority. Okay?
Okay, so thank you.
Maybe you could ask this: why did we have to consider this P2? Okay, you could say that P1 is running. Okay, P1 is running, and P2 is the mutex. P3 has the mutex. P1 will be blocked. So P1 is waiting for P3 to finish the critical region, etc. You could say the same thing. Well, this is kind of easy to see why, because P1 knows that it is waiting for a lower priority, and that one has the mutex, and you could see that, and this is expected. That's why they added this in the middle. Sometimes, I mean, this is simplified. Sometimes there is a chain of processes depending on each other. It is not that easy to see there is a priority inversion happening. Okay, so priority adjustments is this. You might, oh, okay, I'm out of time. Let me, how many slides do I have? Oh, come on. I'm not going to finish this up. Priority adjustment is this. Let me talk about the priority adjustments. If I have high priority jobs, middle priority and low priority jobs, if I have many jobs in the high priority queue and just one or two jobs in the middle and low priority queue, if I keep adding more jobs at the high priority queue jobs, okay, these two jobs and this job here will starve. They will not get the CPU time because there is always some high priority job available. These will not get the CPU time. That's not good. So they thought about this, and they said that maybe we should adjust the priorities from time to time. That's called priority adjustments. So periodically reduce the priority of the running processes. If the scheduler thinks that this process has used too much CPU time, even though it has a higher priority, maybe I will mark this as a middle level priority. Okay. Or maybe if the scheduler thinks that this process didn't get any CPU time for the last second, so I will increase its priority to middle or high level, so that it can get some CPU time. So that's called the priority adjustment. Okay, that's called the priority adjustment, and there are good ways of doing it, and I'm going to show you how to do it in a few minutes, but not today. I think I'm going to do it on Monday. Okay, any questions? Any questions? Okay, if there are no questions, by Monday, read the whole chapter number 2. Okay, that was maybe the most important chapter, along with the chapter number 3, which is the memory management. Read chapter number 2 very well thoroughly, and if you have any questions about chapter number 2, processes threads, ask me on Monday. I hope to finish this chapter on Monday and start talking about the memory. Okay, see you on Monday.
Thank you, sir.